Alrighty, good.
Okay. So we start with a number line, and if we add 1 to like 0, then it just brings us to positive 1. But multiplying by negative 1 would essentially kind of rotate it by 180 degrees. It doesn't translate it over 2 units, it kind of rotates it around 0. And so if we were to do that again, we'd rotate it like 360 degrees. And so we can rewrite this, instead of multiplying by negative 1 twice, we multiply it by negative 1 squared to do a complete 360 degree rotation back to 1. And so what's important is that I squared, which is the square root of negative 1, is equal to negative 1. And so we can, if we go back to this, we can rewrite it as multiplying by I squared rotates 180 degrees. And then we can rewrite that by splitting it in half. Every time we multiply by I, it rotates at 90 degrees. And so, essentially only multiplying by I once rotates it to a point that doesn't exist on the graph, but it does exist on the complex plane. Well, I'll get to that later, but essentially it doesn't exist. What matters is that it rotates at 90 degrees. But what's also important about I is that it like kind of oscillates between I, negative 1, negative I, and 1 when you raise it to powers and stuff. And this will go on forever, and it even works for negative numbers. Can I move this board up?
Yes.
Do I
You pulled down on it.
put it down a little bit?
Yes. Hooray!
That'll work. There we go. Yeah. This is a good marker. So it works for negative numbers, and that's because like I to the power of negative 1 is equal to 1 over I, which is equal to, when you multiply it by I over I, which is equal to I over I squared, which is equal to I over negative 1, which is equal to negative I. And so it works even with negative numbers in school. Where's my mouse? There it is. And so we can sort of get like a visual representation of it with this circle here, which rotates between 1 I, negative 1 I. And so what's to stop us from bringing it back to the line here? And it's the same thing, you rotate by 90 degrees to get to I several times, and you have negative I, you know. And what's to stop us again from drawing another line there to have like 2 axes here? And if we remove the circle and stuff, we get what's called the complex plane, where every time we add 1 for a real number, it goes to the left or the right. But if we add a complex number like I, then it goes up and down. And so if we tried to represent a point like this, then we just add 1 and add I, and so this point is 1 plus I, which, that's just how it works. And so if we bring back the circle here, this circle might look familiar to trigonometry fans out there. It is the unit circle.
I told you.
It has a radius of 1, even in the complex dimension, because I squared is negative 1. So if we move the arrows here, it is the unit circle. And there is a trigonometry equation here that represents all the powers of I, and it's this.
Can you write that down?
I to the
Can you
power of
write that
x is this, and then the x is in front of pi over 2. And this works for any value of I, or x, sorry. And it even works for non-whole numbers of I, like 1/2, which is the square root of I. And it gives us this, which is root 2 over 2 plus I root 2 over 2. If you were to square that, it would give you I. You guys can test it if you want, but it will give you I. It's important to understand that this is just one of of the solutions for the square root of I, but I'll get to that later. And so if we were to graph that, root 2 over 2 plus root 2 over 2I, then it would give us this point here,
45
which lies
degrees.
on the unit circle at an angle of 45 degrees. And so rotating by that 4 times would give us negative I, just
Brilliant.
like we were before. But it's not the only angle that rotated 4 times gives us negative 1. For example, if we had x to the 4th is equal to negative 1, which is where this comes from, then we're looking for an angle that when multiplied by 4 gives us the pi radians, or 180 degrees, so I'm going to say pi. And so this could be pi, or it could be negative pi, because that's the same thing, and also 3 pi. Then we divide by 4, we get pi, over 4, negative pi over 4, negative 3 pi over 4, and there's one more. Negative 5 pi over 4. I guess I'm going into this, that important
You can erase it.
illustration there. But essentially, at all of these coordinates, you just take the cosine of them plus I times the sine of it. And that essentially gives us plus or minus the square root of plus or minus I, which is square root over 2, it's just the coordinates of each of the points at these locations. And so all of them, when raised to the power of 4, will give us negative 1. And so bringing back to e to the power of I pi, it basically just tells it to rotate pi radians along the complex axis to give us negative 1. But why is it e? Well, this next part is up to you guys. So should I explain it the simpler way, or like the way that's the longest?
The longest way.
Okay, the longest way. Here we go.
Just getting out of my.
So this is.
We can get to that. That's the
Yeah,
next
these were the
section.
3 questions on the test
Yeah.
that were crossed out that we didn't have to do. But essentially, the sine of x is equal to that infinite sum. The exclamation mark is factorial. And if you notice, it's all the odd values of x up there for sine, and it oscillates between negative and positive and negative. And for cosine, it's all the even ones, and it also oscillates. But if you look at e to the power of x, then it's all of them, even and odd, but added together. And so it's almost obvious that there's a correlation between them. And so if you were instead of z, if you had I times x, then everywhere that there's an x would be replaced with ix. And so ix squared would be I squared x squared, which is negative x squared. And so that means every even integer would give us a real number, and every other odd one would give us imaginary number, a complex number. And so we can rewrite this by separating all the evens and odds and factoring out I from the odd numbers. And all the even numbers happen to be equal to the cosine of x, and the odd numbers equal to the sine of x. And so e to the power of ix is equal to the sum of both of them,
Brilliant.
which is pretty cool. The short explanation was that on the complex plane here, anything less than e and greater than 1 is going to spiral in towards the middle,
Mhm.
and anything greater than e is going to spiral out towards infinity. And so you have to have e, or else it won't work. But what does this have anything to do with the real world, Why would we use imaginary numbers? Well, they do create what's called a fractal. This is the Mandelbrot set, which involves, I think, an infinite sum of complex numbers. And if you were to zoom that out, it looks like this, which is pretty crazy. I think it's interesting how it repeats itself twice. Actually infinite times, because it goes on forever. But I just think that's cool. Here's another fractal. But aside from looking cool, you can do other things with complex numbers. Like for example, I'm just going to start with this. You need 3 coordinates in real life to describe the location of something, x, y, and z. And so, but the only thing that's stopping me from existing in the same place as Miss Brown right now would be time. And so you need a fourth dimension, time dimension, to describe how we're in a different location. And so really we have 4 dimensions in our world. And in order to make this like less complicated, I'm just going to remove or temporarily ignore the y and z dimensions and keep the x and t, the value of time. And so doing that would give us this graph here. Now I was hoping to be able to draw this on the whiteboard. I don't know if there's enough room. So I guess I'll just do it up here. But I'm gonna go back, sorry. But except on this plane I'm just going to instead of distance as our measurement, I'm gonna use distance over time. Like speed or something. Kind of like how the magnitude of a vector is going to be like meters per second instead of just meters. And so I'm going to use c, which is commonly used as the speed of light. Like just how fast you go. Here, I'm just going to draw this on.
It's great.
So this is the speed, negative speed of light. This is the speed of light. And negative speed of light just means movement to the left instead of movement to the right. And so x value is just movement, and then the t value is time. And essentially, everything exists on this circle here. And for the sake of simplicity, I'm going to just say that the speed of light is 1. So it looks like a unicircle. If you thought we were done with trigonometry, I got some news for you, because everything exists on this circle, on the surface of this circle, and can be represented by a vector. For example, like all of us, we're not moving relative to each other, and so we would be on this vector here, and we all experience the same time. But if I was going half the speed of light in relation to you, then it could be represented by like these 2 vectors here. And so if I was going half the speed of light, then I would only be experiencing whatever this is, √3/2% of the time that you're experiencing. Which it sounds complicated, but it's just that's not important right now.
That's
What
brilliant.
matters is, let's say we had 2 vectors, and this angle here is pi over 4, and this one is negative pi over 4. This is negative pi over 4. They just have the same angle, and we tried to add them together. All right. So this one would have rectangular coordinates of √2/2, √2/2. And this one would have √2/2, negative √2/2. So if we tried to add these together, then the resulting vector, this one here, would have rectangular coordinates of √2, and then these cancel out, right? So that would just give us 0. But this doesn't exist on the surface of the circle. And the equation for the circle is q squared plus x squared is equal to 1, because the speed of light is 1. And so the x is the square root of 2, and the t is 0. And so it doesn't work. And so instead, we're just going to temporarily ignore that this is 0. And do root 2, this is the x, plus, let's just have some value, let's have a t, is equal to 1. So 2 plus t, sorry, that's not enough. T squared is equal to 1. So t squared is equal to negative 1. And so we're going to have to use our friend's imaginary numbers to get t is plus or minus I. And what that means is, on the complex plane, if this is I, this is 1, this is negative I, then we have a vector here with a length of the square root of 2, but a magnitude of 1 because it has I. And there's another one here, but that doesn't really matter. In the real world, it doesn't end up looking like this. Instead, it ends up looking like, and take this with a grain of salt because I'm not a physics major or anything, but in the real world, it ends up looking